Optimization problems. Optimization problems are finding the maximums or minimums of functions, of applied functions, of hopefully real world type of things that actually happen functions. Now, we'll start with a few made up ones just to get in the swing of things, and then we'll try to move on to things that, somebody as a job, as an engineer or physicist or something might actually do upon occasion. Okay? And the guidelines for solving optimization problems are at the bottom of page 219. You have to identify all your given quantities and the quantities to be determined. And if a drawing seems appropriate, make a drawing. And that's not as easy as it sounds sometimes, to even realize what you're given, much less what it is you're supposed to find. Write a primary equation for the quantity that is to be maximized or minimized, and then they have some geometry formulas for you inside the front cover. And reduce the primary equation. Well, step 1 and step 2 don't necessarily have to be done in that order. You can do step 1 first. You say, well, how can you write an equation if you have identified all the quantities to be determined? Well, you may just say, okay, I know I'm given this. I can write this down. I know it's right. Might not be useful. Sometimes I write things down that aren't useful accidentally. Don't do it on purpose. Okay? So you may just start by writing an equation. For instance, if you're dealing with the volume of a sphere, well, you may just write down the equation for a volume of a sphere, and maybe you don't end up using it. Probably you will. Okay? So step 1 and step 2 go together, I guess is what I'm trying to say. It's not necessarily one before the other. Okay? Once you get this primary equation, quite often it's going to have more than one variable in it. We don't want that. So sometimes we have to come up with a secondary equation that may help us transfer to having just a single variable. I know that doesn't make a lot of sense yet. You'll see it when we do an example like that. Okay? Domain comes into play here because if you're doing an actual application, quite often you don't need negative numbers in your domain. Okay? If you're building something, you're not going to have a negative length of something, that kind of thing. Okay? So the domain comes into play. So determine whether or not you have a domain besides negative infinity to infinity. And then once you've done all this, the whole point is you're trying to find either the maximum or the minimum. The problem will state which it is you're supposed to find. Okay? So an optimization is either finding the maximum or it's finding the minimum, whichever one is optimal. Okay? Because sometimes, depending on what you're doing, you may want to make sure that you have a minimum something. Okay? You're building a container, you may want a minimum surface area for a certain amount of volume. All right? On the other hand, you may have a certain amount of material to work with, and you want to maximize the volume you can make with that material. Okay? So sometimes you want to minimize, sometimes you want to maximize. Don't forget that if you do have endpoints, you got to check them. So we can do, quite often we'll do the second derivative test. If the second derivative's, easy to get, we'll do the second derivative test. But if it's the first derivative test or second derivative test, whichever, if our domain has endpoints, we got to check those too. Okay? All right. Here at the bottom, you see all of the notes that I had for this section, because it comes down to working problems. Okay? This is one of those cases where, in theory, you have all the tools necessary. I could give you the assignment and walk away. In theory. In practice, you need to see a couple of examples. And then after that, you've got the tools. You've got to figure out how to use them. I can't figure it out for you because there's not enough examples in the world. You know what I'm saying? Every problem's a little bit different. Every problem presents its own issues. So you've got to, man up or woman up and work your way through these. Let's do one. Let's start on page 223 with number 2. An open box of maximum volume is to be made from a square piece of material 24 inches on a side. By cutting equal squares from the corners and turning up the sides. So look at the figure. What you've got is you've got a 24 by 24 square. And then the way you turn that into a box is, if you look up here on the screen, see, cut this little edge out, cut that little square out there, and there, and there, and there, and now you can fold those flaps up to make it a box. So this edge, this rectangular flap, for lack of a better word there, becomes one of the vertical sides of the box. You see what's going on? Okay. Now, the bigger the square you cut out, then the higher or the bigger the height of the box. Making sense? See what I'm talking about? All right. So here's what our task is. Analytically, complete 6 rows of a table such as the one below. The first 2 rows are shown, and use the table to guess the maximum volume. Then we'll get into the actual process of doing the optimization. So, because you've done this kind of thing in previous classes, haven't you, where you tried to find the maximum of something, and you probably did it with the table? All right, it still works. Not always practical. Okay? So, here's what we do first. Well, let's look at let's just copy down their first 2 rows of their table. So we have the height as the first column. All right, so we've got height as the first column, then the length and width, because the length and width are the same, right? Because it's a square to start with, and we're cutting out a square on each corner. The length and the width are going to be the same. And then the volume. And for a rectangular prism, the volume is length times width times height. Okay? The length and width are the same, and then the height. So when the height is 1, the length and the width, all right, if they start off 24, and then you cut 1 inch from each end, so you take off an inch there and an inch there, isn't the length or the width, whichever way you're thinking of it now, 24 minus, then you cut off 1 inch at each end, so 2 times 1. So that's how we get the 24 minus 2 times 1. Okay? Then the height is 2. Well, then the volume then, the height is 1 times, and then the length and the width are the same thing, so they just said squared instead of writing it out twice. Make sense? Well, then when the height is 2, so now you take the 24 inches, and you're cutting off 2 inches at each end, so it's 2 times 2 that you're subtracting to get the length and the width. Then the volume is the height of 2, then 24 minus 2 times 2 squared. That's the length times the width. That squared. You with me? So what's the third line going to look like? Write down your third line. Does it look something like that? Then I'll do the arithmetic for you. That's 972. Fourth row. You get 1,024 for that volume. Go ahead and do the last two rows and see if you end up with what I end up with. So do we all have the same 6 rows? And you can get the final volume just up here from me, 980 and 864. You with me? All right. So what does the maximum volume seem to be? 1,024 looks like the maximum volume, doesn't it? So we can write the maximum volume seems to be 1,024. And the only reason I'm saying seems instead of is because, not the whole wide world runs on integers, right, or whole numbers. So it's possible that the maximum is actually, somewhere between 3 and 5 is pretty obvious, but it may not be exactly at 4. It could be 4.0003, right? Okay? So it seems to be that. Everybody with me? Part B. Write the volume V as a function of x. All right, so now we're going to try to get our primary equation. Okay? Now, our unknown is how much do we cut out? So we can either think of that unknown as the height, because once you fold it up, that is the height, or just think of it like the book does here as x. So x is the amount you cut out. So look where x shows up in every one of our little rows here. There's x, 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 x. Well, isn't that x and that x? There's x, there's x. So in our volume, isn't our volume going to be something like, let me even call it v of x to emphasize that volume is a function of x in this case. How would you write that? X times 24 minus 2x quantity squared. Does that seem reasonable? Okay. Now, do we have any domain issues here? It has to be positive. All right. So our domain, and I'll write this a little more neatly here in a minute. It has to start at 0, doesn't it? Can't be negative. Can't even be 0. Does it go to infinity? What's the biggest it could be? Yeah, in fact, it can't even be all the way up to 12, could it? Because if you've got 24 inches and you cut 12 off each end, you don't have anything left. Okay? So it's got to stop right before 12, doesn't it? Okay. Yes. Yep, we sure can. And we'll probably run into one of those. All right, so there's our function that we're going to maximize, and we know what the domain of it is. Part C says, use calculus, so that's very specific, to find the critical number of the function in part B that we just wrote, and find the maximum value. All right, so that's not real specific, but that's okay because we know how to do this, don't we? We know how to find the maximum of a function. We're going to find its derivative. From there, we'll find the critical numbers, and then we'll do a test. Maybe we'll decide to do the first derivative test. Maybe we'll decide to do the second derivative test, but we'll do a test. So, take the derivative. I decided to just to leave it the way it was written. I could have multiplied that binomial out first and then done all that, but I didn't. Maybe I should have. I don't know. So, first function, x times the derivative of the second. To take the derivative of the second, we've got to chain rule it. So that'll be exponent times coefficient. That's how that 2 gets out there in front. Then the quantity, 24 minus 2x. Subtract 1 from the exponent. 2 minus 1 is 1, so the new exponent is 1. Then times the derivative of the quantity. Well, the derivative of 24 is 0. The derivative of negative 2x is negative 2. That's the first half of the product rule, and the chain rule was inside of that, plus the second function, 24 minus 2x quantity squared, times the derivative of the first. And I didn't write it down, but what's the derivative of x? Yeah, it's just 1. So I didn't bother putting times 1. All right, we good there? Let's do a little multiplying. In front of the plus sign, I can multiply the x times the 2 times the negative 2 and get negative 4x times 24 minus 2x. And then behind the plus sign, there's really nothing to do. I'm kind of wishing I'd just multiplied all this out to start with, but I didn't. So now what can I do? Well, there's a lot of things I can do. So instead of me asking you that, let me show you what I did, because there's a lot of things I could have done here. I factored out a 24 minus 2x. So, from in front of the plus sign, what I have underlined in blue, divided by 24 minus 2x, I'm left with negative 4x. From behind the plus sign, what I have circled in blue, divided by 24 minus 2x, leaves me with the 24 minus 2x to the 1. So I get that. With me? Simplify inside your bracket. So I've got 24 minus 2x times negative 6x plus 24. And I can factor some constants. I can factor a constant out of each of these parentheses. So I'm going to do that. I'm going to factor a negative 2 out of the first parentheses and a negative 6 out of the second parentheses. So finally, my first derivative is positive 12, negative 2 times negative 6, times the quantity x minus 12, times the quantity x minus 4. Okay. Now, what are my critical numbers? Not 0. 4 and 12. Are both of those in our domain? Just 4. So x equals 4 is the critical number. And I did write in 12 is not in the domain. On the AP test, do that. Okay? Because you don't want them to mistakenly think that you didn't realize that 12 made the first derivative equal 0. So tell them that. All right? I'm not going to make you tell me because I'm not. But tell the people on the AP test that you knew 12 could have been a critical number if it had been in the domain. Okay? All right. So we've only got one critical number, and I can do the first derivative test. However, I'm a little scared of it, and here's why. We're really, really used to starting our interval at negative infinity, aren't we? But where would we have to start this one? 0. And we're really, really, really used to ending our last interval at infinity. Where would we have to end this last interval? 12. So if you can remember that, fine. Make your interval from 0 to 4 and the next one from 4 to 12. I don't really trust myself that much. I'm going to write down negative infinity to start it and infinity to end it, and that's going to screw everything up, and I'm going to think I have a problem I can't work when I do have a problem I can work. So instead, I did the second derivative test. So we got to get the second derivative, which isn't as bad as you think it's going to be. Use the constant multiple rule, so it'll be 12 times, and then you're thinking, oh, but that's going to be hard. No, it's not. Product rule it. First function, x minus 12, times the derivative of the second, and what's the derivative of x minus 4? 1, plus the second function, x minus 4, times the derivative of the first. And what's the derivative of x minus 12? 1. So it actually works out kind of easy. Do what? So work inside your brackets. X plus x is 2x, negative 12 and negative 4 is negative 16. I can factor a 2 out and get 24 times the quantity x minus 8. All right, and here's what I love about the second derivative test. I can do the second derivative test in my head. Now, what I need to write, so let's do the second derivative test in our head. Take the second derivative, or take the critical number, take the critical number 4, and substitute 4 into the second derivative. Do you get a positive second derivative or a negative second derivative? Negative. And when you have a critical number where the derivative equals 0, and the second derivative is negative, do you have a relative maximum or a relative minimum? A relative maximum. What were we trying to find? A maximum. We were trying to maximize the volume. So here's the way I write it out. I'm just stating that I'm using the second derivative test. The second derivative, when x equals 4, v double prime of 4, means the second derivative when x equals 4. And then I didn't even have to write out that it equaled negative 96. I could just write out is negative. Okay? Isn't that the second derivative test? There it is. Okay? It's not in the chart anymore, but that's okay. If I had several critical numbers to check, I'd still put it in the chart. But since I just had one and I could do it in my head, all I really got to do is write down the answer. Okay? But I got to state that it's the second derivative that I'm using, especially on the AP test. Well, on my test too. I'll make sure you have to do that. Okay? All right, so what do we conclude from all this then? Our whole point was to find the maximum volume, and we found it. So V of 4 equals 1,024 is a relative maximum. You got to put that. You got to put the 1,024. Because the question didn't actually ask how big the square should be that you cut out. It asked what's the maximum volume. Okay? So make sure you give them that, the maximum volume. All right.
Why have you done all the second derivative tests? Because we already find the relative mean not happening. So we're
Right.
going to set V4 is a relative maximum without having one I know.
I'm glad you asked that. How come I couldn't just say, once I got here, that that must be where the maximum occurs? Because it's the only critical number. It can't occur anywhere else. Why can't I just say it there? It could have been a minimum. What if we set up a function wrong? See, if our function's wrong, it might give us a minimum instead of a maximum.
But this one, you can't go, I mean, you can think about the graph.
Where's your graph? All right, but this is my point. What if I made the function wrong? See what I'm saying? So I see your point. Is if we have the correct function, well, here's another thing we got to worry about. What if the premise of the question is wrong? What if this volume can't be maximized? All right, because see, I could make, if I had to make up a problem off the top of my head without thinking it through, I might make one up that actually can't be worked, right? Because not all functions have a maximum. So what if I made up a problem that led you to a function that didn't have a maximum, and I asked you for the maximum? So it is kind of just a check, but it's an important thing to do, especially if you're not sitting in calculus class. You're sitting in an engineering class, and you're asked to maximize something. Well, what if it can't be maximized? That's worth knowing too, isn't it? If the whole premise of your big project that you're taking to the boss is to maximize this certain thing, and it can't be maximized, you want to know that before you take that to the boss. Okay? So, I see your point. It's a valid point, but we need to do this because we need to make sure we're right. You don't want to be one of those guys that has to fake the data afterwards to make it look right. Make sense? All right. What's the last thing they tell us to do here? Graph it. Oh, Lord. Okay. This is going to be fun. I mean, yeah, well, did the sarcasm come through there? I meant for it to. Because with the maximum being 1024, that's not going to show up in your normal standard window. All right, so we have y1 will be x parentheses 24 minus 2x, close the parentheses, put an exponent of 2 on it, and hit graph. Okay, so let's change our window. We need to go, the x coordinates need to go from 0 to 12. I don't even know how to do the scale thing. I know I ought to do that. I don't really know how that works. The y coordinates need to go from 0 to 1,025. And there's our graph, which looked like that when I tried to copy it. See how good I am at copying? Yeah, that's before I learned how to take a screenshot of that and then print it off and tape it onto my paper. I'll learn that eventually during the year. You'll see a difference. Can we have a woohoo? That was kind of a weak woohoo, I must say. All right. Number 4. Find 2 positive numbers, don't say integers, numbers, that satisfy the given requirements. The product is 192 and the sum is a minimum. All right, 2 positive numbers. What would you like to call these 2 positive numbers? X and Y. And what's, but I wrote X and Y. And what is it that we know about these 2 positive numbers? They equal what? So let X and Y be positive numbers, and P equals X times Y equals 192. Can anybody guess what the P stands for? Product. Excellent. Does not stand for price or presence. All right. What are we supposed to, what are we supposed to do? Find the sum and make it a minimum. So, if our 2 numbers are X and Y, what's their sum? Well, I know, but in symbols, what's their sum? X plus y. So, the first equation we wrote down was not our primary equation. That's our primary equation. That's the one we have to minimize. So we need the sum, which is x plus y, to be a minimum. So S is a minimum. Now, we don't want two different variables. So choose one. Choose X. You are just ornery. So we're going to turn this into a function of X. So S of X equals X plus Y. And keep in mind, that's what we have to minimize. Now, that means we need to turn the Y into an X. How are we going to do that? We could use magic, but I didn't bring the wand today, so, and Hermione's not here. How about taking that and solving it for y? If we do that, since x plus y, nope, since x times y equals 192, that means that y equals 192 over x. So what can we replace y with? So S of x is now x plus 192 over x. No, because that'd be multiplying both sides by x to do that. All right. So what do we want to do if we want to get the minimum for this? Find the derivative. S prime of x equals, well, the derivative of x is 1, and that 192 over x, the way I thought of that is 192 times x to the negative 1, and then just did the power rule on it. That'd give me 192, negative 192 x to the negative 2. But that's hard to find critical numbers written like that. So I'll change it to 1 minus 192 over x squared. It's still hard to find critical numbers. So think of that 1 as x squared over x squared. And if I think of that 1 as x squared over x squared minus 192 over x squared, doesn't that become x squared minus 192 over x squared? Now, I know I'm going fast, but we're running out of time. So you with me? All right. To find the critical numbers, where the derivative does not exist would be x squared equals 0. You get x equals 0. Can x equal 0? No, we didn't write the domain out in the little parentheses notation, but they told us right off the bat that they're positive. So x can't be 0. It has to be a positive number, okay? But where the numerator equals 0 is going to give us our critical number. So where x squared minus 192 equals 0 gives us our critical number. Now, technically, when you solve that, you'd get plus or minus the square root of 192, but it can't be the negative one. All right, and I pointed that out. Now, I fairly much trust the authors of this book, and if they say that this function can be minimized, I more or less trust them. But what if they're evil? It's always a possibility. There have been lots of evil mathematicians in the world. Okay? I don't know if this function can be minimized just because they say so, so I need to do the test. Second derivative test, once again, is easiest here because the second derivative is easy to get. If we use that version of the first derivative, that's the easiest version of the first derivative. What's the second derivative? All right, but is it negative 384?
Positive.
Positive. So the second derivative is 384 x to the negative 3, or 384 over x cubed. All right, so mentally, let's do this. When you substitute a positive square root of 192 in x, do you get a positive second derivative or a negative second derivative? Positive. So we can say this. S double prime of the square root of 192 is positive, equals positive, I wrote. Therefore, S of the square root of 192 is a relative minimum. Now, I want to make sure I give the correct answer to the question. The direction said to find two positive numbers that satisfy the given requirements. We don't have to tell them what the minimum is. We have to tell them what two positive numbers satisfy the requirements. We know one of them, all right, x is the square root of 192. But how many numbers did we have? We had two. We had a y. So we need to figure out what y equals. Now, y equals 192 over x. I got that from there. So doesn't that mean y equals 192 over the square root of 192? And what is 192 divided by the square root of 192? Square root of 192. So both numbers are the square root of 192.
This person was the square root of 192.
Yeah, it does because of that right there, doesn't it? So finish it off. Tell them the answer. The sum S is a minimum when x equals the square root of 192 and y equals the square root of 192. When I'm grading your quiz, don't leave me guessing that you know what you did. State it. Don't be afraid. Say it. You will find some of these a bit challenging.